Now I'll share the screen. All right. Tips for visual observing and some other crackpot theories. I'd like to point out that this talk is for beginners, at least in the beginning. I'm going to talk about eyepieces. That's a religious war. So for those of you at home, if you hear fist fighting, it's because we have disagreements about the perfect eyepieces for observing. But I'm going to talk about eyepieces for a little bit, and then I'm going to get in and talk about how I observe a couple of objects and explain my technique, and then explain an amazing discovery that I made from a book that I bought 32 years ago. So I want to show you some of my telescopes. That's to entertain you, but also to give you an idea of the equipment that I'm working with. This is a 6-inch f4 Newtonian that I built. It's called a richest field telescope, and you haven't lived until you've been in a dark sky site with a 6-inch f4 and cruised up the Milky Way. Hang on one second. Man, I cannot. Okay, I want to be able to mute people because there's something. Anyhow, 6-inch f4. This is a 6-inch f6 that I built and made the mirror for. The design is by Richard Berry, who is the editor of Astronomy magazine. What's cool about this scope is you store it in the garage with the telescope pointing up, and you grab the top handle and pull the tube off, and then you reach down and grab the bottom handle, and wow, that, whoa, I'll never find it. And you can lift the base up, carry it outside, plunk it down, and you're ready to go. I was having a conversation with Sam Storch this afternoon, and I got to tell you this. Sam showed a picture of my telescope to someone in Florida. I don't know, maybe he had it on his phone or something. And the guy says, it has a square tube. And Sam said, yeah. And the guy said, what happens when you look at round objects? Does it cut the corners off? That's like, okay, that's a classic. I love that. This is an 8-inch f4, and I made the mirror for this one. Very portable scope. So you'll notice that most of these are short focal length scopes. They're not 2000 millimeter or 2500 millimeter Schmidt-Cass. The 6-inch f4 is on the left, and on the right is a 10-inch f4.8, which I built. I purchased the mirror. It was a club purchase back when we used to make 10-inch f4.8 scopes. And then this is a 4-inch 106 millimeter f6.5 Astrotech. I'm here because I was doing the transit of Mercury. And then this is my baby. It's a 5-inch f8 Starfire, which I bought back in 1989. I don't think I could afford it now. It's on a Super Polaris DX mount. So you can see the focal lengths. The 6-inch f4 is 609 millimeter. That's the shortest. And the longest is the 10-inch f4.8 at 1219 millimeter. And the Starfire is 1016 millimeter. So those are still shorter focal length scopes. So generally, I'm getting lower powers and wider views. I want to look at some eyepieces. So, oh, yikes. I need to, I knew that if I messed with that. Sorry. Yeah, right. Are they still? Let's see. I think it won't matter for most of the things. So this is a view, not my picture, of the Pleiades. So there's three generally different eyepieces. This will be the less expensive. So it's a Plossl eyepiece. I'll do this. This is with a like a super wide, like a Nagler. This is like a Panoptic, and this is a Plossl. So this is all at the same power, but the angular field of view of the eyepiece is narrower. So when you look in the eyepiece, you're seeing about a 52 millimeter angle from one side of the field to the other. So Plossls are about a 52-degree field of view, apparent field of view. It has nothing to do with what the telescope shows you. It's like the difference between looking through a short toilet paper tube or a longer towel paper tube. The hole is smaller in the towel paper tube. So this is a 52 millimeter Plossl field of view. This is the field of view in a Panoptic, which is 68 degrees. And this is the field of view in a Nagler, which is 82 degrees. So, gee, why wouldn't you want all Naglers? Well, because of their cost. But just to give you a sense of the difference between Plossls, wide fields, and super wides like Naglers. I love this shot. There's a difference between these two eyepieces. There are several differences. One of them is focal length. The one on the left, the smaller one, is a 6 millimeter eyepiece, and the large one is a 20 millimeter 2-inch Nagler. One of the other differences is the cost. You can buy that Plossl, the small one, for about 49 bucks. And I think the 20 millimeter Nagler runs about 400. I think they don't make it anymore. But I love this. I mean, come on, give me a break. Look at the difference in size. So starting from the left is a 6 millimeter Nagler, a 9 millimeter Nagler. I'm sorry, 6 millimeter Plossl, a 9 millimeter Plossl, then a 26 millimeter Plossl. Next to it, a 7 millimeter Nagler, then a 22 millimeter Panoptic, which is partially wide angle. You saw that, that was the middle image. And on the right is a full Nagler, which is 82 millimeters. One of the things I wanted to point out, and this is going to be difficult because I don't have a pointer, but look at the eyepiece on the left and notice how small the eye lens is. It's tiny. The 9 millimeter is larger. The 26 millimeter, which is the third one from the left, has a nice big eye lens, easy to put your eye on. And next to that is a 7 millimeter Nagler, and that has a surprisingly large eye lens. And then the 13 Nagler and the 20 millimeter Nagler. So here's a top view. I bought a 6 millimeter Nagler early on with one of my first telescopes, and it's almost impossible to look through. You have to get your eye so close to the eye lens. You really can't look through it if you have glasses. And you're so close to it that your eyelashes and the oil from your eye act like an oil brush and brush across the eye lens and then help make things blurry. The 9.7 millimeter is easier to look through because the eye lens is larger. The 6.4 is impossible. And it turns out it's about 3/16 of an inch. I mean, that's crazy to try and look through that. So here's the interesting lesson. The 6.4 Plössl is at the left and the 7 Nagler is at the right. And it's like, wait, that's about the same focal length. How come the eye lens is bigger? Well, because the Plössl costs $49 and the 7 millimeter Nagler costs about $330. But after a while, you may feel that you want one of those just because it's so much easier to look through. One other thing you can do, this is a Barlow lens, and I think this is a 3 times, I forget. And what it does is multiply the power of the eyepiece you're using. So here's a 26 millimeter Plössl in my telescope in place. And here it is, you take the lens, the eyepiece out and put the Barlow in. And so it's a 3 times Barlow. So you divide 26 by 3 and you get about 8.8 power. And the beauty is, if you remember the Plössl, it had like a 3/4 inch eye lens. So
I think I left it upstairs.
I'm sorry. So you get 8 power, and yet you have a large eye lens to look through. So you can make a high-powered eyepiece that's easier to look through if you add a Barlow lens, and they come in about 2 power, 2.5, 3 power. Yes.
Just, I know what you're saying, but just for clarity, you misspoke. You meant you get an 8 millimeter eyepiece, not an 8 power.
I'm sorry. Yes, thank you. So you divide the 26 millimeter by 3, and you get 8.8 millimeter eyepiece, which is a higher power. So, yes.
I'm sorry. I forget now with the Barlow, though, aren't you sacrificing field of view to do that?
No.
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 No more than if you put an equivalent entire field of view 8.8 millimeter eyepiece.
Yeah, but the some fields you can go from, like with a Nagler, you can go from 80.
No, but the Nagler has a Barlow in it. I should explain that, by the way. The secret of the Nagler is that 7 millimeter Nagler to the right. You know what a 6 millimeter Plössl looks like? That 7 millimeter Nagler is maybe a 21 millimeter focal length with a 3 times Barlow built in, and you divide 21 by 3 and you get 7.
I think they call them Smythe lenses when you put them inside the eyepiece.
Okay, so what makes the Naglers amazing is they have a built-in Barlow lens or something to that effect, and you have great eye relief. You have a large eye lens. Eye relief means your eyelashes don't brush up against the eye lens, and it also means if you wear glasses, as I do, it's very easy to look through it. So after I bought one of every focal length in my first 5 or 10 years, maybe first 5 years of observing, because I didn't know any better. And then eventually I settled down and figured out what I needed. So these are my most used eyepieces in all of my telescopes, from the 6-inch f4 Richfield to the 10-inch Newtonian or the 5-inch f8 Starfire. So it's a 22 panoptic, which is a wide field. It's not a Nagler, but it's a wide field. Then I got a 13 Nagler, which is about half of the 22 millimeter in focal length, which means it's twice the power. And then I bought a 7 millimeter Nagler, and that's about half the focal length of the 13, and that's twice the power again. So if I use it in my 8-inch f4, 813 millimeter, I have 37 power, 63 power, and 116. And people are liable to say 116, that's the highest power that you use. And if I were splitting double stars, I'll tell you I cheated. I do have a 5 millimeter Nagler, but I tend not to use it that much. It increases the power, but I don't think it's as sharp an image. So anyhow, relatively low powers for what I do, which is not doing double stars. So this is the best part. I'm going to read to you because I have no memory. To stand beneath the dark, crystal clear, moonless country sky is an awe-inspiring experience. Those thousands of stars, many larger than our own sun, can make us feel small indeed. It seems possible to see to infinity, though we cannot reach beyond arm's length. The beauty of the universe defies description. Turn a telescope on a seemingly empty part of the sky and swarms of new stars come into view, and possibly a faint glow of a fuzzy nebulosity. Yet the heavens are subtle. Imagine the fuzzy patch at the threshold of visibility is really a trillion suns, a galaxy larger than our own, in which our sun is but a tiny speck. Incomprehensible, yet somehow we try. Seeing that galaxy firsthand, even through a small telescope, is much more inspiring than the large, beautiful photographs on the astronomy book back that we see indoors. Nothing can compare to viewing the universe directly. Direct viewing, at least of the deep sky objects, is now mainly for those interested just in beauty and inspiration. The typical amateur astronomer today has a telescope with a main mirror or lens, 4 to 10 inches in diameter. A modern instrument of this size often provides a more detailed view of deep sky objects than the larger telescopes used by pioneering astronomers to make the great discoveries of the past. A telescope with only 6 inches of aperture gathers about 400 times the light of the unaided eye. So these beautiful but dim objects can be brought into view. So I'm going to talk about how I observe the Lagoon and Trifid Nebula. They're gaseous nebulae in the constellation, up above the constellation of Sagittarius. So the Trifid is at the top of this photograph and the Lagoon at the bottom. This is the Lagoon. I mean, what an astounding thing to look at. And that's the Trifid. Man. Oh, that kills me that that covers up something that I need there. So the Lagoon Nebula is Messier 8. It's a giant interstellar cloud in the constellation Sagittarius. It is classified as an emission nebula and an H2 region. It's about 4.6 magnitude, faintly visible to the naked eye. I love going to Stellafane every summer. The skies are dark enough to see that. And the Trifid Nebula, the one that was higher up, It's an unusual combination of an open cluster of stars, an open cluster of stars, an emission nebula, a reflection nebula, and a dark nebula that divides the emission nebula into 3 parts. It is a star-forming region. It's 6.3 magnitude. There is so much to see here that it's not even funny, and these are astounding objects to look at. Oh, okay. 24, 13, and 7 sequence. So I begin observing these things with my 24 panoptic, which is a wide field eyepiece, 68-degree field of view. It's low power. I use it as my first eyepiece to find objects along with a Telrad. It gives me an overview of the object because it's wide field, and it gives a sense of context. What else is in the field? Then I take that out and put in the 13 Nagler. It's an 82 field of view. It gives me a closer view. It gives me more detail, and the internal structure of what I'm looking at is more evident. I take that eyepiece out, and I'm probably spending 5 minutes at least with each eyepiece, carefully looking. Then I put in a 7 Nagler, takes me closer yet with even more detail. And it's interesting, and I can't explain this, or I couldn't explain this before a couple of days ago. The object looks different in each eyepiece, and I didn't understand that. I mean, yeah, I'm looking closer, but the object looks different. The detail is different. And I wasn't sure why that is, but it's a system that I came up with to go through that sequence of eyepieces. After viewing with all 3 eyepieces, then I do it all again using a UHC filter. And I'll talk about this filter. It's a filter I use on all my telescopes. And it stands for ultra high contrast. Can you read that?
Yep.
Okay, because I don't want to have to narrate it. But the UHC is the first filter that you should buy. It increases contrast of the nebulosity. It blackens the background. It filters out some street lights. It's unbeatable for revealing nebulosity. So there's all the technical stuff. And I'm using Lumicon only because when I went looking for the information, I first bought Lumicon filters and I still have them. They had the best explanations that I could copy for this. So then if I'm using my 8-inch scope, maybe, or my 10-inch scope, I go through once again, but this time I take the UHC off and use the oxygen 3. That really dims the object, but it also brings out more contrast within the object. A lot of times the 8-inch, I lose too much light, so I'll only use the oxygen 3 on a 10-inch scope. And I go through that cycle again of wide, medium, and close. So if you look at the Lumicon this way, it looks like a mirror. I'll spare you this, but that tower in the center is what light is allowed in. Oh, I should see if I can read this. Starting from the left, the things that are blocked are mercury vapor. Then on the other side of the tower, mercury vapor, air glow, auroras, high pressure sodium, mercury vapor, low pressure sodium, high pressure sodium, air glow, and aurora. And then hydrogen alpha is the second peak on the right. So this is actually a Meade nebular, broadband nebular filter. I'm sorry, the question?
Would this be considered a light pollution filter?
It's more than that. I think there's a lighter version of this.
Because I see the high and low pressure sodium, I'm assuming they're trying to attenuate.
It does that too.
School street lamps.
Yeah,
Yeah,
right.
The problem
Um,
is that the street lights are now all LEDs.
Full spectrum.
Yeah,
So
full-
most light pollution filters don't do anything anymore.
Right, but I'm wondering if this still will.
um,
It's essentially the same.
Well, because.
as
you don't
long
have
as
any
they're,
mercury vapor light out there anymore. You don't have any high pressure sodium light out there.
I
anymore.
think there's still some out there. I don't think they've switched right away, but just to get a rough sense, and it does darken the background too.
What those filters do though, with the LED lights, it blocks out all the wavelengths of light except for the most sensitive wavelengths, 496 and 501,
Mhm.
those filters. So, you'll be able to see the object better. The only thing is I haven't explored the LEDs enough to see the impact on it. It's still, even with LEDs, it's still gotta be better.
The reason I made the distinction about a light pollution filter versus this, which you're calling ultra high contrast, is because the light pollution filters were designed specifically to block those sequences. Mercury vapor, sodium vapor. That's not the purpose of this filter.
No, I make the UHC filters. The only difference between O3 and UHC filters, is the UHC filters are wider bandwidth. It allows more of the light goes in, but the UHC filters they're both light pollution filters. The only difference is that the O3 filter is actually better filter.
Okay, so the O3 filters on the left, they both look like mirrors when you look at them by reflected light, but by transmitted light, they have different colors. And what's also interesting is I have TeleView versions of this that Tony made, and they have different colors when you look through them like this, but they're great on the sky. So I've told you the story of how I observed something, what eyepieces I used, and then I made an astounding rediscovery. This book, Visual Astronomy of the Deep Sky by Roger Clark, came out in 1990, published by Sky Publishing and Cambridge University Press. I think it was $40. Within a year or two, it was out of print, and people would meet people on dark street corners to buy it and pay $150 for the book because it's such an amazing book. So this is what's astounding. We will see that the eye is more sensitive to faint extended light source if the light is spread out over about 5 to 10 degrees. Because the ability to see low contrast features in faint objects depends on their angular size, the visual observer will detect different amounts of detail at different magnifications. What they're talking about is that the human eye has the central part, which is called the fovea, and that's cones. And if you think cones begins with a C, that's where we get our color vision in bright light. Around that are rods, and those are the ones that detect low light, and everything we look at with rods, we see in black and white. We don't see color. So what they're saying is that the light needs to be spread out to 5 or 10 degrees in our eye, so we take in enough of the rods to see the faint objects. I get to read to you more. Don't steal my thunder. Okay. where am I? So, after reading many of the handbooks, this is, by the way, all this reading is from that book of the visual sky. After reading many of the handbooks for amateur astronomers available today, I found a surprising lack of information on observing deep sky objects or what can actually be seen of them through telescopes. The typical handbook devotes considerable space to observing the moon and planets, but when the subject of galaxies and nebulae comes up, it has less to say. Usually it just recommends that because these objects are faint, low power should be used. Such works have inculcated the idea among amateur astronomers that one should have a richest field telescope and low power eyepieces for deep sky work. This concept seemed wrong to me. My impression at star parties in the dark skies of the Cascade Mountains of Washington State was that an 8-inch f10 telescope gave a more detailed view of most objects than richest field telescopes of the same or even slightly larger aperture. No one could give a good reason why such high focal ratio telescopes seem to work better on faint objects. Doing research for this book, I found the answer. The impression that high F ratios by themselves give a better view is largely wrong. The true reason is partly what this book is about. The magnification used, not the focal ratio, determines what can be seen in a very faint object. The magnification used, not the focal ratio, determines what can be seen in a faint object. A higher focal ratio telescope simply yields higher power with a given eyepiece and therefore is more likely to be used that way. We will see that the eye is more sensitive to faint, extended light sources if the light is spread out over about 3 to 10 degrees in the eye. Because the ability to see low contrast features in faint objects depends on their angular size, the visual observer will detect different amounts of detail at different magnifications. Holy cow. I mean, I'm not smart. I just somehow figured out that by using 3 different eyepieces, I got the best views of the different objects. Just to do that again, because the ability to see low contrast features in faint objects depends on their angular size, the visual observer will detect different amounts of detail at different amounts of magnification. I'm a genius, but I had to go back to a book I bought 32 years ago to find that out. Increasing the magnification spreads the light over more receptors in the eye. And this is what's fascinating. When we look at something, we think, I look at that and I see that. Well, not really. The eye gathers the data from that. It goes into our brain, and then is processed. And that's where optical illusions come from. The data comes in and the brain is going, what is that? What is that? And then usually it figures it out, but sometimes it doesn't, and it makes you think it's something else. So increasing the magnification spreads light over more receptors, and the brain's processing power can then bring into view fainter objects having lower contrast. Like, how cool is that? The brain is processing that if the image is spread out over more of the cones. Another interesting concept is how the optimum magnification for a given object varies with the size of the telescope. Since the surface brightness of the object, it's less in a telescope of smaller aperture. 3-inch telescope, much less bright than a 6-inch telescope. Since the surface brightness is less in a telescope of smaller aperture, the optimum power is actually higher than that for a bigger telescope. This applies only to deep sky objects. Another new concept is the highest magnification that may ever be usefully employed on a telescope. It is normally accepted that the highest power is about 50 to 60 times the objective diameter in inches. You all know that, right? So if you have a 3-inch telescope, max power 150 to 180 power if the seeing is good. So that's normally accepted. This limit of 50 to 60 times per inch is correct only for bright objects such as the moon and planets. This blows me away. For fainter object, the eye has less resolution and needs to see things larger, so higher powers are called for. At the limit of the eye's detection ability, the highest useful magnification is on the order of 330 power per inch of objective. It's like, are you kidding? I mean, I have to try this because this sounds crazy. Yeah. The highest useful magnification is on the order of 330 per inch of objective. These extremely high magnifications are useful in specialized cases, such as detection of detail in small planetary nebula. This is the thing that blows me away. Increasing the magnification spreads the light over more receptors. The brain's processing power can bring into view the fainter objects with lower contrast. The optimum magnification for a given object varies with the size of the telescope. That's like heresy, it seems. Two other techniques. One is called averted vision. I think most of you know what it is. I'll leave this up so you can read it. But essentially, if you look directly at an object, what you're using is the cones, which only work in bright light. If you look just to the left or right of the object, the fovea comes off the object and the cones are where the object is projected into the lens, and you will see the object better. It becomes a little brighter when you avert your view to one side or to the other. Sometimes I go top, bottom. I found this fascinating. This technique of being able to see dim lights over long distance has been passed down over hundreds of generations of sailors whose duty included standing lookout watches, making one better able to spot dim lights from other ships or shore locations at night. And the other, it explains why averted vision works. And the other thing that is sort of counterintuitive is telescope motion. I've never heard of it this way, but it's called scope rocking. And it's done by simply moving the telescope back and forth slightly to move the object around in the field. This is based on the fact that the visual system is more sensitive to motion than to static objects. And I have been in dark sky sites, or maybe Custer, and I know I'm right on something because the Telluride is on it. And maybe it's M1, for instance, the Crab Nebula, which is hard to see and if you don't have really dark skies. And I'm not sure if something's there. So I just push on the scope a little bit just to shake it. And suddenly you go, holy cow, look at that. It's very faint and you're not sure it's there. And the minute you just bounce the scope a tiny bit, you see this circular dim thing move and you realize, wow, it is there. So scope rocking, it is. And it's a very useful technique for deep sky
I
objects.
wonder if that would be equally as effective on refractors as it would be like.
I think so,
It is.
because it's about the eye's ability to detect motion.
Okay, so that's what you mean by the visual system of our eyes, not the telescope.
Right, right. It's that if you have what seems like a black field and you can't tell if the thing is there, sometimes just a little push on the scope. In this case, you'd have to use a hammer on the 16-inch, but that hint of motion is, so I love this quote in The Graduate. Dustin Hoffman's father says about a harebrained scheme to, Dustin Hoffman, seems like a half-baked idea to me. Dustin says, oh no, sir, it's fully baked. So you wonder about my crackpot theories. None of what I told you is a crackpot theory. I was just using less than truth in advertising to get people to come to this talk. One of the absolute joys of the summer Milky Way is to begin at Sagittarius, the teapot, and cruise up from the horizon along the Milky Way using my lowest power eyepiece. The views are sublime as clumps of stars and various Messier objects move through the eyepiece field.
That's the steam coming out of the pot.
That's it. And that's it. Now, if only, oh man, here we go. I guess I just hit us.
Stop recording.
Man. Okay, here we go. And let me stop recording.
You did not stop recording, you canceled stopping.
Oh.